Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Welcome, or hopefully welcome back to the Reliability Matters podcast. For those of you who are keeping score, this is episode number 114. On this show, we've discussed many aspects of the electronics assembly process. We've talked about reflow, thermal management, printing, soldering materials, additives, and so much more. What do all these topics have in common? When done correctly, they all contribute to the reliability of circuit assemblies, hence the name Reliability Matters. Today, we're going to dive into the subject of cleaning circuit assemblies after reflow. For many assemblers, the cleaning process was replaced by the use of no-clean flux technology. Time and technology have eroded the concept of allowing all residues to remain on the assembly for many manufacturers. Today, residue-caused failures are such a concern that IPC recently and radically changed the way circuit assemblies are considered to be clean. My guests today are Sal Sparacino and Eric Camden. Sal is Director of Sales at Zestron Americas, located in Manassas, Virginia. Zestron is a manufacturer of cleaning chemicals for the electronics industry. Eric is a lead investigator for Foresight, an analytical laboratory based in Kokomo, Indiana. Eric's the guy you call when things go wrong. Together, with my experience as a cleaning equipment manufacturer, we'll discuss how cleaning contributes to increased reliability, and we'll review the reasons cleaning has returned as a mainstream assembly process. So without any further ado, let me welcome Eric and Sal to the show. Hey, fellas.
Hey, Mike. How you doing, Mike? Thanks for that introduction.
You are welcome. Thank you guys for agreeing to be on the show. I really appreciate it. I owe you a drink or 10. So this almost sets up like a joke, you know, three cleaning guys walk into a bar and go from there. One of Maslow's theories is that if all you have is a hammer, you see the world as a bed of nails. And if all you are is a cleaning person, you tend to see the world through the lens of something being clean or something being dirty. So I don't know if that's unique to me, but I would assume you kind of view the world the same way. Let's talk about cleaning. There's a lot of subjects we discuss on this show that relate to how clean boards are, that relate to reliability. We talk about reflow, we talk about printing and soldering materials, failure analysis, standards, and all that. And cleaning is definitely one of those new again mainstream topics that has come back to relevancy. So I thought it would be a good idea to grab two of my favorite experts and let's talk cleaning for a while. So cleaning from a historical perspective, we'll start there. I always like to go back in my Wayback Machine, the time machine. I started in this industry in 1985, and for the most part, with very few exceptions, every circuit board was cleaned. And one of the exceptions was television sets, old-fashioned tube CRT type television sets. They tended to use a real heavy solids rosin flux, and they never cleaned it. It's kind of a poor man's conformal coating. Outside of that, and maybe a couple other low-end applications, boards were all cleaned. It was just a matter of practice. It was a protocol. But then, of course, something happened that we're all aware of in 1989, which was the signing of the Montreal Protocol, which was a treaty which effectively banned the cleaning solvents that were common in our industry, 1,1,1-trichloroethane, Freon TMS, and a bunch of generic versions of those. And we had two choices then. It was a 10-year phase-out. So from 1989 to 1999, we had some decisions to make. One decision would be to change solvents or change cleaning medias. But our industry was blessed or cursed, depending upon who you are, with an alternative technology, and that was the use of a flux, probably aptly named at the time, maybe not so appropriate today, called no clean flux. And the idea was the residues would be invisible, and the invisible residues would be benign, and you could throw away your cleaners and not ever have to clean again. And that was the promise, and that promise was kept for at least a couple of decades for most people. I think it's quite interesting that there were a few groups of manufacturers that did not buy into that, one being the military world, the aerospace world, the medical world, basically people who built things. If they failed, people would die, or there would be a great cost. They didn't buy into that philosophy of not cleaning. But that's only a small percentage of the electronics industry. Consumer stuff, class 1, class 2, IPC class 1, class 2, not mission critical. Most of the electronic manufacturing falls into that realm. And those folks all said, throw out the cleaners, and they embraced, rightly so at the moment, this concept of not cleaning the boards after reflow. So let's talk about that for a little bit. What factors would you say contributed to the success of no clean flux and not having to remove any of the contaminants that are on the board? And what factors contributed to or are contributing to that practice no longer being quite as relevant as it was before? I'll turn that over to either Sal or Eric, and let's just go for it.
Well, I'll jump in here. I started here at Foresight, at the time CSL in actually January of 2000. So I came in right after no cleans were starting to become adopted throughout the industry. And what we saw from a lot of our customers, they were thrilled. Like you said, we don't have to clean. You can take the cleaner off the floor, and, in that same space, they can put another line. So, I think, being able to expand your assembly capability without expanding your actual footprint of your facility, I think was a big selling point for a lot of companies. And, and I think that was a good thing at the time you mentioned, but, as they kept up with, miniaturization, they saw other issues come along where maybe that wasn't going to be, practical for all of their different parts that they were producing. So, early on, what I saw, was a lot of customers taking their inline wash equipment off the floor and replacing it with another line or, different inspection equipment, whatever it might be. They all of a sudden had 32 more feet on an already jam-packed line. And, think back to 2000, there was a lot of, assembly going on, everywhere around the world was really starting to expand. I think back, early 2000s. So I think, every square foot that they could scavenge, I think was going to be very important for that, particular CM.
Yeah, I'll just chime on to that, Eric. Just a couple more points here. One thing that stayed, right, because there were still people that were using water-soluble stuff, right? So going back to those times, you're still cleaning water-soluble with water, right? But then going back to Mike's question, what's changed? Well, what's changed, and Mike, I know you talk about this very often in a lot of webinars I've seen, as well as my own company here, the board geometry has changed tremendously in the last 10 years, right? So things are getting much more densely packed, stacked components and these types of things. And, kind of what worked 15, 20 years ago, be it water or not, is not necessarily working today. And which kind of goes back to my company, if I can just say it this way, we weren't even in the electronics business in the 80s as Zestron, right? So Montreal Protocol basically opened a window, and we are one of the companies, one of a few that recognize, that, hey, we understand we got this no clean thing, but as you pointed out, Mike, there's a number of people that in the high rel space, and I think a phrase that you always use that I like to take from you is risk tolerance, right? when that risk tolerance, you know, if you don't have a high risk tolerance, you need to know that your electronics are going to be, quote unquote, safe to use in the indefinite future. You know, that kind of brings us, you know, I'm sure we're going to get to the failure mechanisms, you know, things like that. But yeah, so those are just, you know, a few of the comments there. You know, so water is still an issue, and the need to clean is as big as ever today.
Yeah, I should have pointed out that was also one of the alternatives. It wasn't just clean or not clean. One of the alternatives was switch to a water-soluble flux and use water to clean it. Now,
Right.
a lot of people did that. Of course, back in the day when pretty much all boards were cleaned, the cleaning method was primarily conveyorized or inline cleaners. As Eric mentioned, you know, they saved 30 feet of floor space when they got rid of that process or more. I remember Linda Woody from Lockheed. She designed her own cleaner. You know, they call it the Woody cleaner. And it was 40 feet long. I just can't imagine. And I think it was all stainless steel, if I recall. It was a beast. But back in the day, when everything was cleaned, there was a need for volume, and conveyorized or inline machines, you know, fit that volume need. When for other applications that were military related or medical or aerospace, which are traditionally not consumer volumes, you know, they're dozens of boards, not thousands of boards. The most common method for them was vapor degreasers, which would boil the solvent, and the board would be cleaned in the boiled solvent and then rinsed effectively in the vapor area. And the fly in the ointment was when they pulled the basket of boards out, they released that vapor lock, and chlorine molecules escaped up to the upper parts of the atmosphere and chewed on ozone like Pac-Man. And,
Right.
And you know, scientists were afraid that would create a lessening of the ozone layer, and you know, we've had several terms for environmental issues. It used to be ozone depletion. You know, that's what caused the Montreal Protocol. That's why we're all talking. Then it went to global warming, and now it's climate change. You know, I think people held the environmentalists' words specifically. You know, they said, "You said global warming. It's chilly. It's chilly." Right. So climate change. So let's bounce around a little bit. Sal, you talked about people using water to clean, which was definitely an alternative. Cleaning today requires a method, obviously. That method could be manual. That method could be automated. If it's manual, it's usually a can of aerosol solvent and a scrub brush, basically. That method is relegated primarily to rework and repair. So we're probably not going to spend too much time on that because that's fairly self-evident. Automated versions go from immersion cleaners, modern vapor degreasers running solvents that have yet to be banned, some of which are on the ban list. It's kind of like the FBI's most wanted. Eventually they get caught, right? So, but the number of sheer volume of solvents that could be used since the Montreal Protocol has been reduced, not for CFC reasons, but for other environmental reasons. The most popular method from a production standpoint seems to be water-based systems. Now, there's a misconception when people say water-based systems because they're saying, well, I'm cleaning a rosin flux. I can't clean that with water. But water-based systems are not necessarily and not commonly just water. Sal, walk us through what the chemicals do in a water-based system and how they work with water.
Sure. Yeah. No. It's good question, Mike. So think of it this way: that what we're cleaning, the residues, the soils, whatever, however you want to describe them, they're polar and non-polar in nature, right? So, and the things that are polar in nature obviously can be cleaned with water, right? Like dissolves like. Always think of it that way. So what we do, as in our company as well as others out there, we make what's called an engineered aqueous-based, water-based cleaning agent. And now these water-based cleaning agents do have I'll call it a solvent constituent, if you will. So typically we're running somewhere in call it the 10% range, 12% range, 13, something like that, in terms of the concentrate chemistry or the engineer solution that gets homogenized within the water phase itself. And together, really what that does, and I think I sent you a chart, Mike. Let me think of it this way. When you look at water, water has a specific surface density or surface tension, if you will, right? And think about, substrates, these electronic substrates that customers have. There's a lot of components on a board these days, right? I know, Mike, you always show pictures of boards circa 1980 in an iPhone today. And you look at what we call the standoff height, or some people call it the Z height, if you will, of a component from the substrate surface. These days, we're talking somewhere around 1.5 to 2 mil. So water has a high surface tension. And I know that's a bit of an eye chart there, but essentially water is somewhere in the 70 dynes per centimeter surface tension. And if you heat it up, it goes down a little bit. It drops down to maybe the mid to low 60s or thereabouts. Now, these water-based cleaning agents, or these aqueous-based engineered cleaning agents, effectively, they reduce that surface tension. And when that surface tension is reduced, it literally enables the cleaning solution to interact with the residues that are on the board. And here's another really important point. So, going back to the chart, if you will, Mike, the cleaning agent surface tension drops you down to 30 or to the high 20s. So less than half of what it is with water. But now think about this. The cleaning solution has to contact the residue. And when I speak with customers often about, cleaning technology, and again, I don't care if it's a batch cleaner or an ultrasonic cleaner or an inline cleaner, but let's just say a mechanical cleaning device in general, there's 3 things that really need to be optimized. And this is the way I think of it, as I'm talking to customers and analyzing what their challenges may be. First of all, there's what I call the chemical energy. So in other words, do we have the right cleaning chemistry? Do we have the right cleaning agent that's going to solubilize those residues? So that's really number one, right? And again, it's like dissolves like. There's lots of different solder paste out there, fluxes and so on. Rosin, no clean, water-based, synthetics, and so on, right? So we, as a cleaning agent supplier, need to make sure that, we're matching the cleaning agent so that it has a solvency to dissolve those residues if it can get in contact. So that's number one, the chemical energy. Number 2 is thermal energy, right? The temperature is impactful, right? Just think of just washing your hands, right? Are you going to wash your hands with 30-degree water, or would you like to have 100-degree water in your sink, right, with soap, right? It does make a difference. And the last thing, which is equally important, or maybe even more important, depending on the machine, is what I call the mechanical energy. In other words, how are we delivering that solution to the surface of that board, right? Because if we can't contact the residue, then there's no way to solubilize and there's no way to get it out. So going back to your question, having a cleaning agent that has both polar and non-polar constituents, that will ensure, if we provided we know what the different solder paste and other chemistries the customer is using, that'll ensure that we can solubilize those residues. We're matching the cleaning agent to that. And then by looking at the machine and what we call, we use the phrase over at Zestron a lot, optimizing, making sure that we're picking that sweet spot between concentration, am I going to run it at 10%, 12%, concentration, temperature, am I going to run it at 120 degrees or 140 or 150? Obviously, for a cost-effective solution, we want that temperature to be as low as possible. We want the concentration to be as low as possible.
You want to come close to boiling it so it all goes up the stack and you can deliver more and more and more. Come on, get real.
Oh, you're killing me, Mike. No, but you know what to say. Yeah, I mean, it's all about the value proposition we're delivering to the customer, right? And then we match that with the optimization of the machine, right? Working with guys like you and your team and other equipment suppliers out there, making sure we understand the type of nozzles you use and the spray pressures you use and the number of bars you use and all those types of things, and we optimize that. And that's how we can deliver, a sweet solution for a customer.
Excellent. I'm going to ask Eric a question in just one second, but I want to hit on something that you said. and that was, delivering the cleaning material to the part and energy and things like that. One thing that I miss, frankly, I used to sell vapor degreasers, back in the 80s. And one thing I miss about the vapor degreaser technology was that the solvent did the majority of the work. What you needed to do was expose the soils to the solvent. And since it was an immersion process into boiling solvent, the total amount of energy that was required to dissolve or solubilize the soils was provided by the chemical. The chemical was heated, obviously, because it's boiling. And all the operator had to do was dunk the basket in, count to 30, and pull it out. And the boards were virtually guaranteed to be clean, or at least clean enough. The chemicals that are used today, the water-based chemicals that are used today, don't work on contact. I remember early in the no clean days, and then a little later on when people started coming back to cleaning, never experiencing an aqueous-based chemical, they would run a trial. They would basically take a solvent, drop a droplet of solvent onto a slide that has flux on it, and set their stopwatch and see how long it took to dissolve. And then they would do the same with an aqueous chemical at ambient temperature with no energy and just contact. And all they would do is make the flux wet. It wouldn't solubilize. So some people just said, oh, this stuff's no good. Look at, solvents are so much better. What they didn't realize was that there's an extra dynamic other than contact. It takes energy. It takes mechanical energy, because the modern chemicals, and I'm preaching to the choir here, Sal, because you make those chemicals, but for the sake of our audience, the modern chemicals that are used today that are dominating the cleaning world don't work on just contact. They require folks like me and other manufacturers to deliver those chemical products with sufficient energy to force the solubilization process or saponification process, depending on the technology, to work. They don't work just on contact. So it takes contact, it takes heat, it takes mechanical energy to all work in a symphony to create the solubilization effect that can then be rinsed off afterwards. Eric, one of the things that I talk about a lot is the decision to stop removing flux was also a decision to stop removing everything. And I think that fact was lost on a lot of people. I advise in my workshops and webinars and papers, I always advise people to not think of it as a defluxing process. Because if you're calling it a defluxing process and you're buying defluxing equipment from me and defluxing chemical from Sal to run a defluxing process, and then someone tells you the flux is fine, problem solved, right? Check. You don't have to do it. But really, I think the block a lot of people have is it's not a defluxing process. Yes, it is, but it is more importantly a cleaning process.
Right.
Because there are a few other, to say the least, a few other residue species on an assembly beyond flux. Eric,
you mean the usual suspects?
The usual suspects. Thank you. Yes, the usual suspects. You are a lead investigator for an analytical laboratory. Your job is to find dirt and expose it and find the root cause of it and provide solutions.
And how to eliminate it. Yeah.
How to eliminate it. What are the types of residues? I mean, your lab has all this analytical equipment. You have ion chromatography and surface insulation resistance testing and all sorts of cool gadgets to analyze what the soils are. From your experience, what are, besides flux, that's the given.
Sure.
Besides flux, what are the other contaminant species on a board when the flux is allowed to remain due to a lack of a cleaning process?
Right. So, I mean, we've gone over this, a lot of different times, and it's not just the flux. You're choosing to leave everything in place from the bareboard manufacturing process, from the component manufacturing process, from handling, packaging, any other materials that might come in contact with the PCBA. So, the different residues, if it were just flux, it would be a lot easier to handle. But considering the plating process, PCBs, and even with the component manufacturing process, we've done a lot of different failure analysis studies here, over the years. And, a lot of times we find it's not the flux, the component manufacturing process, it is almost a microcosm of the PCB fab process. So you've got plating, you've got to do neutralization steps with components, you got to do, good rinse after the plating, or, because we've seen, we've seen cases where there was a fantastic, manufacturing process using a no clean flux. They were seeing the right temperatures, the right dwell times, everything required to render all those residues near benign, and they were still getting failure on some components. You can go ahead and show that photo, that cap. This was what the customer was, coming to us and saying, we've got this failure. Well, this had nothing to do with the the assembly process. It had everything to do with the process of that component manufacturing. So they weren't being properly neutralized and rinsed after the plating process. So, this was never taken care of with wash process, as if you're using a water-soluble flux.
And for the sake of our audience who are driving in their cars, with a little FOMO because they can't see this picture, this is a picture of a surface mount capacitor with a dendrite. We'll explain what that is in a moment, growing right across the surface between the polarities. On top of it, yes. And going from one polarity to another, from a cathode to an anode. Explain for those who are not aware, what is a dendrite, what causes dendrites, and what harm do they do they provide on an assembly?
Sure. So dendrite, or electrochemical migration growth, is basically a deplating cell that pulls metal from the cathode to the anode under power. So to grow dendrite, you have to have three conditions have to be present. You have to have moisture, you have to have voltage differential, and you have to have some sort of conductive residue. In the case of this capacitor with the dendrite growing on top, it was part of the metallization process that was left in place and not properly rinsed. So, what happens is, during the growth of electrochemical migration, you can see intermittent failures depending on the amount of available atmospheric moisture, depending on the amount of voltage going across cathode to anode, but eventually you'll have a dead short because you've basically grown a trace from one pole to the other. So, this is where we see, most of the failures that are sent into us. I would still say the vast majority are related to cleanliness, and we see electrochemical migration or some similar effect like that from leaving, active residues on the board, regardless of the source. That I always say, we're not looking for flux residue, we're looking for ionic content, and we'll figure out where it's coming from. What we like to do, background samples on the flux and kind of compare it to the results on a failed board and say, okay, this is most likely the flux residue. Let's look at thermal profiles, things like that to optimize that process. But it could be from a number of different things. The water used, for the PC fab rinse, if they're not using good quality water there, it could be leaving, calcium, magnesium, something, tap water. We've seen several cases where a PC fab shop was using just standard tap water, really dirty tap water. And so they were, making a fine product and then making it dirty before they sent it out the door. So, yeah, when you decide not to clean, you're not just deciding not to clean flux, you're deciding to leave all process residues in place, on your final assembly. And then when that goes out in the field, plug it in, a little bit of moisture, you're going to find out how dirty it is.
Yeah, a lot of times when I speak at, public events, at conferences and symposiums or whatever, sometime, I'll talk about no clean, and when I'm done, inevitably a flux manufacturer will come up to me and take issue with my comments on not cleaning. Sure. and they're trying to assure me, and they're showing me proof that their flux is not that conductive, it's very little residue, and the residue is relatively benign. And ironically, sure, I agree with all that.
100%.
They're 100%. That's not my issue. My issue is the totality of all of the residues. A little bit from flux, a little bit from component fab, a little bit from board fab, a little bit from dirty humans, a little bit just from all the conveyors these machines go through.
Right.
All of that in totality raises the stakes. Now, one of the questions I'm asked regularly is, why now? No Clean had a very successful run. Again, as I said earlier, the military and high-rel people, they stayed away from it, which I'm grateful for. I fly a lot on airplanes, and I'm very happy to know that those boards were cleaned. But for the most part, the commercial industry, the consumer industry, they got away with not cleaning for a long time, and arguably, it was successful. The boards were reliable. We're seeing in the last several years an avalanche of issues, failures, and reliability issues related to electrochemical migration, ECM. You talked about dendritic growth, which is the dramatic version of ECM. That's what creates the sparks, the soot, in some cases fire, things like that. There's also parasitic electrical leakage, which is a temporary problem. It's not really enough to grow a dendrite that you can see, but it's enough to reduce the resistivity, which normally doesn't cause the drama. It doesn't cause things to catch fire, but frequently it causes things just not to work properly. Like you can't calibrate a board. It just won't.
No trouble founds are most often, they end up finding some parasitic leakage somewhere. So it's not bad enough yet, which is, that's the worst case, really. It works sometimes, it doesn't sometimes. So we start talking about parasitic leakage, a lot of that's dependent on, the duty cycles and the amount of available moisture on that. So that dendrites, and those are the ones that really drive people crazy because they don't have a hard failure.
Right. And unlike dendritic growth, dendrites grow until they stop growing. And they stop growing when the conditions are not right for them to grow, like enough moisture. Then the moment it's returned back to a harsh environment, they grow a little further, and eventually, their goal is to reach the finish line and short out. At least one good thing about dendritic growth is you can see it. You can put it under a scope, and you can fairly easily see it. Parasitic leakage is invisible. You can't see it. It's just this invisible path of little bits of current that are allowed to flow in an otherwise dielectric part of the board, right? The board loses its dielectric properties, basically, its resistive properties. The frustrating part, as you alluded to, Eric, with no trouble found, NTF, is that parasitic leakage will only occur when the conditions are optimal. When a customer can't calibrate a device in the field, they send it back to the factory for investigation or repair. The factory, of course, has a climate-controlled environment. It's no longer exposed to a harsh environment. They troubleshoot it. Everything calibrates perfectly. The device operates perfectly. They issue it a no trouble found. They ship it back to their customer. The customer uses the product in a moist environment, a humid environment, or otherwise harsh environment, and it fails again. And you get this going back and forth. I like Doc Brown. I had him on this show a while ago, and he said that you should never refer to it as no trouble found. You should always think of it as trouble not found. And that I thought was sage advice, because no trouble found says there's no trouble. Trouble not found means, we agree there's trouble. We can't find the source, so you keep looking.
Right.
I think there's an even better acronym for no trouble found, and that instead of NTF, it should be WTF. And we'll let that lie right where it is, because it's a frustrating problem. The engineer on the other side thinks the manufacturer's incompetent, and the manufacturer thinks the customer's incompetent because they can't duplicate the problem. So why now? Why did we have such a good run with no clean and not cleaning? And what are the factors, Sal, that are driving reliability issues, that are driving electrochemical migration through dendritic growth and parasitic electrical leakage and other things? What's changed? Why is our magic wand not working anymore?
Well, I'm going to start out with something that's pretty interesting. It's called Moore's Law. I don't know if you find this in a textbook yet, but basically it's attributed to Gordon Moore, the co-founder and former CEO of Intel. And basically what it says is we can expect the speed and capability of our computers to increase every 2 years. And because of this, we're going to pay less for them. But to do that, what's happening at the technology level, right? For most of this podcast, we've been talking about surface mount technology, right? Which is where this industry really took root, back in the 80s, 90s, and whatever, right? But, componentry is changing. Semiconductors, single ICs and so forth. So things are getting more complex. And when they get more complex, you're putting, port densities increase. I alluded to this before. And even there's another phrase these days, it's called hybrid microelectronics, where literally it's the merging of surface mount and semicon technology to be able to do what Gordon Moore was talking about, was to be able to give you the computing power that you get on an iPhone, or that we have on this this podcast today. Like when I was in high school many years ago, we didn't even have calculators, right? I mean, this is a fun fact. I'll put this out here. I was the first class in my high school that did not learn a slide rule, because the year that I was there, like it was at the TI, whatever it was back in those days, the algebraic calculator, it was it was coming out, and schools allowed you to use that. Well, look at the electronics today. And Mike, I sent you another picture, right? I mean, I just want to kind of make the point about how tight the gaps are on componentry today.
And for the sake of our audience, for the sake of our audience, we're showing several photographs of common everyday things and the relative size of those things.
Right. So I said, I mentioned earlier that on the SMT side, we're in the realm of, maybe 50 microns, right, is the gap, and even in some cases less than that. A human hair is 75 microns. So just think about that for a second. How thin is that, right? And it gets back to the surface tension argument we talked about a little bit ago. And then when you get to some of these microelectronics things, like copper pillars and things like this, the spacing between these things, you're talking about 40 microns. I mean, it's literally, tiny. So, bacteria is 5 microns, just to give you, another snapshot. So in answer to your question, Mike, I'd like to use your phrase, the risk tolerance, right? So, think of where computers are used today. Think of, not just phones. Think of the EV industry, the electrification of automotive, of cars, right? There's more computers in a car than, today than ever before. And these things are built with highly sophisticated components in the semicon industry, creating these hybrid microelectronics. The spacing is so tight, and it gets back to the whole cleaning argument we've been talking about here. Everything that Eric talked about, all the different types of residues, let's call it, those polar and non-polar, residues that are on these, on these boards. The gaps are so tight, so close, that unless you have an engineered cleaning agent of some sort and a machine, as we talked about before, that's where you're able to literally, optimize those energy sources to contact the residue, solubilize that residue, and then rinse it off that part.
I'm going to go back to that. I'm going to go back to that photograph just for a moment, because I want to make a point here. The typical diameter, if you will, of a coffee ground, right?
Yeah, it's true.
Is 355 microns. The typical size of a grain of beach sand is 250 microns. As you mentioned, Sal, human hair is 75 microns. I didn't even think that this would be measurable, but smoke consists of tiny particles that are about 10 microns in size. Obviously you can't see that. In fact, I think 50 microns is the limit for visual. You can't see anything small. The human eye cannot see anything smaller than 50 microns.
Well, it sounds about right, because a hair is 75.
Hair is 75,
right?
and you clearly can see that.
Yeah. Right.
I know my wife can, because if I have a hair on my shoulder or something, she can see it from 10 feet away and come over and pull it off. by bacteria, as you mentioned, is 5 microns. The standoff height below a QFN is about 2 microns, sometimes 1.
2 microns. Yeah,
that's smaller. That would be the most sterile environment to be in, because if you can get under there, bacteria can't fit, right? Even bacteria can't fit under there.
Sure.
Yet, you have to get, or we, the equipment people, have to get your juice under there to clean, right? Which is quite a feat, and hence your comments earlier about the surface tension reduction properties of a chemical additive, because how can you clean under a 2 mil standoff with 70 dyne water? Yeah,
right,
I call it
exactly.
I call it chasing skinny water with fat water. It's very challenging to do, and every manufacturer of equipment has their own technique. Every chemical company has their own version of surface tension. I'm going to ask you some questions about pH in just a little bit, because you guys have done some novel things with pH that kind of go against conventional wisdom, at least historical conventional wisdom. But before we do that, one of my favorite subjects is things that go wrong. And one of my favorite people to talk to about things that go wrong is Eric, because Eric he has a whole career finding things that go wrong. And Eric, tell us some tales from the crypt. When you go out and do an investigation, you're like a CSI, you're like a crime scene investigator, right? Sure. And you're looking for the bodies and the murderer and the murder weapon and all that stuff. So tell me a story or two that you think would be anecdotal for this topic.
Sure. One of the things I'm seeing actually more and more these days, and we can certainly expand on this, is cleaning of no cleans. Understanding how to do that. So when we go see a customer, they've sent us a failure, and we've done the ion chromatography, we've done some, localized extractions, we've done some SIM, whatever it might be. And what we find out is, they have an ineffective wash process for the materials they're trying to clean. So as Sal mentioned earlier, you've got to have that mechanical energy. You've got to have the contact time for the chemistry, to be on the board. You can't wash at 4 foot a minute. You cannot wash under a QFN, no matter how much concentration you're using of what chemistry you're using. You can't wash at 4 foot a minute. You have to give that chemistry time along with the thermal energy, and the mechanical energy to really do its job. So, what we see, with many customers is the cleaning of no clean, where they, where they're just not doing a good job. They were cleaning water soluble just fine with that 15 years ago. So we're plugging the machine back in, and now we're going to, try this new flux. Flux is flux. So, what I'm finding, this tales from the crypt thing, what I'm finding is, a lot of higher ups and along the manufacturing line have determined that they hear the word no clean, and they're not worried about leaving anything behind. If they don't do an effective cleaning job, they just think, well, it's no clean flux. It doesn't matter if we leave residues behind. Instead of actually knowing how no clean flux works, you've got this outer shell, a poor man's conformal coat. Basically, at this point in time in the industry, and when you remove that outer shell from that no clean flux, now all of a sudden you've exposed everything that's going to readily absorb moisture and set up those, ECM, pathways and start that electrical leakage path. So, I see so many times out there where customers are, they're okay. Now our customers saying we have to wash something. We're just going to use the same profiles and everything we did exactly the same way as 15 years ago when everything was through hole. Well, not 15 years ago. Still even 15 years ago. We're nowhere near the surface mount technology that we have now. So we've lost a lot of that clearance that we had. That we weren't worried about. 2 micron standoffs 15 years ago. It didn't exist really, outside of some very specialized parts. This is some of the early, package on package stuff maybe. But, now I just think people, they tend to lean on what worked a long time ago, thinking it'll work today, when, working in the failure analysis and process qualification side of things, we know that's absolutely, just not the case. So, when we get out there and we see, people being a little laissez-faire about, what materials they're using, and they figure, oh, well, it's all no clean, so I'm not worried about putting, extra. I got a large thermal mass component, so we'll just, double, triple the amount of flux I'm going to put on the board, and then use that same profile, not thinking, well, and going back to what you said earlier, Mike, a lot of times, even especially with us, from our side, we hear it from flux manufacturers. Well, you're saying that, our flux is dirty and this, that, and the other. And I've never said that a flux is a right or wrong material. What my job is to go to the customer and say, can they process that material in a way that leaves it, in a near benign state as you have manufactured it. So it's not a material qualification, disqualification, from our side of things most of the time. It's a process qualification, not a material qualification. So can we optimize your, reflow? Can we look at your wash? Whatever it might be, to handle the materials that you have chosen. So, it's really getting out there and making a mindset where people aren't swapping chemistries all the time, cleaning or flux or whatever it is, and say, let's work with what you have, with the equipment that you have, to figure out how to get these failures out of here. Because, we see a lot of times zero failures. And those are, usually the easiest ones to diagnose, because it'll be something fairly obvious. We'll have it narrowed down to a trace, to, a single line or a part, whatever it might be. You can usually work backwards from that, looking at the assembly process, looking at the equipment and all that, but there's just so many, we've always done it this way still out here in the industry. And, working from the failure analysis side, that's great for the bottom line, but, we need to get this education out there, let everybody know, everything has changed in the last 10 years. If you don't keep up, you're just going to keep, piling up your scrap pile, and your customer returns and satisfaction is going to go down.
Yeah, there's an awful lot of cause and effect in our world.
For sure.
Every world, actually.
Sure.
But certainly in our world, a lot of cause and effect. One of the things that I think I talked about changing the mentality from calling it a defluxing process to a cleaning process. The other, if this was the world according to Mike, the other thing I would pronounce is don't call it no clean flux, because no clean flux presumes you're not going to clean it. And if you are cleaning a no clean flux, it just sounds like you're doing something wrong, right? And
right.
I like to refer to it as a low solids flux, because that's exactly
what it is.
It's a low solids flux. Now, I talked to one flux manufacturer several years ago, and he said, of all people, flux manufacturer, no clean flux does not mean don't clean. It means if you are not going to clean, this is the species of flux you need to run. The only species of flux you can run if you're not going to clean. Obviously, if you're not going to clean, you wouldn't run an organic acid flux, an OA flux, because that would be like leaving battery acid on your board. You wouldn't leave even an RMA on the board with the component spacings and standoff heights we have today. That would be disastrous. That would be instant ECM. But no clean doesn't mean don't clean. No clean is just the species appropriate for not cleaning. I found, I don't know about you, Sal and Eric, most of our customers, a pretty good majority of our customers, are cleaning no clean. And
hands down.
Yeah. And we like to conduct polls when we do our webinars. Now, keep in mind, people on a cleaning webinar are probably cleaning or interested in cleaning, so that changes things a little bit. But we ask our attendees once a year, what's the most common flux you use? And by far, it's like 80-some-odd%, it's no clean. And then we ask, if it's no clean, what's the percentage of your no clean flux that you clean? And the last poll was 56%. 56%, more than half of the boards they reflow using no clean flux are cleaned. Now, on the face of it, it sounds like, well, they must be doing something wrong. But there is a great advantage to sticking with one flux for your production needs. Rather than saying, okay, we're going to run a water-soluble flux or a different type of flux on stuff that's going to be cleaned, and we're going to run a no clean on stuff that's not going to be cleaned. There is this phenomenon called engineering changes. And I can't think of the last major engineering change a flux manufacturer has developed for water-soluble flux. It wouldn't surprise me if someone told me that water-soluble flux formulations haven't changed in 20 years. That wouldn't surprise. I don't know if that's a fact, but that wouldn't surprise me if it was. It also wouldn't surprise me if I learned that the last change to a no clean flux formulation from the manufacturer was no more than 20 minutes ago.
Yeah.
It is constantly evolving. I think there's more data on no clean flux in terms of reflow profiles and printing techniques and specs, release and slump, and all the things that people look at when they're evaluating a solder paste. I think there's more available data and research on no cleans than any other species of flux. And that's because no clean represents probably 80-85% of the market. So it makes sense to run the most engineered, the most up-to-date, the most supported, the most understood soldering material, and then clean what needs to be cleaned. If it doesn't need to be cleaned, wonderful, don't clean. Go have a good day. Someday, it's like the angel of death, in the Bible, the angel of death. You can paint. Cleaning is is akin to putting lamb's blood over your door, right? The angel of death will pass you by. In this case, the angel of death is electrochemical migration. But eventually, as boards are engineered with components much, much closer together, and boards are more frequently placed into harsh environments, IoT, thank you very much, electrification of cars, thank you very much. We're just pushing all this stuff out there. Everything's a connected device now, and a lot of those things are a harsh environment. And that is just driving down the tolerance for residue. And that is driving up the need to remove those residues to ensure that your assembly is reliable from an electrochemical migration standpoint. Now, Sal, I've been on this planet a long time. I've been in this industry 37 years, and I remember the early days of saponifiers when there were always solvents and there were always these saponifiers, and they were in the early days. I'm talking about 80s. They were relatively awful products, meaning that if you cleaned for 8 seconds too long, your joints would all come out black. They had a super high pH. They had no buffering technology. And they would damage a part quite rapidly. You would never put an aluminum heatsink into a cleaner with those types of saponifiers because they would just come out pitted. But the reason they had to have a high pH is because the whole process of saponification works by reacting with a high pH chemical, causing a chemical reaction to the low pH acidic flux and converting it to soap, which is saponification. And then during the rinse process, the soap can be rinsed away.
Rinsed off.
It wasn't truly solubilized in the manner that I'm familiar. I'm not a chemist, but the way I use the term solubilization, that's not really a solubilized material. That was the old saponifiers. So I kind of grew up, cut my teeth with the idea that you need a high pH. Every chemical on the market, water-based defluxing chemical, cleaning chemical, was high pH. And all of a sudden, you guys come up with a 7 pH, a neutral. And that just went against my understanding. So two questions. How does a neutral chemical remove flux? What's different about it? And two, what are the advantages of running something that is pH neutral versus something that is traditionally 10 or 11 or whatever the higher pH numbers are?
Sure. So let me try and address it this way. So you're absolutely right. In the early days, whenever, go back 80s, 90s, whatever, high alkaline cleaning agents were basically the norm, right? But as you said, when you get into things like anodized aluminum and other types of sensitive metals and whatnot, you can get etching, discoloration, tarnishing, and so on. So those high pH cleaners chemists would add what we would call inhibition packages, essentially, right? So they would add some other, soup to the mix to prevent any kind of dulling and surface, not contamination, but surface degradation, if you will, right? And it works well. I mean, we actually have those cleaning agents, and they're widely sold today as well. However, over the years, and again, my background is not, I'm not a chemist here, but we have our PhD scientists over between America and over in Germany. These guys put their heads together and said, there's got to be a way to get a pH neutral cleaning agent to be able to solubilize, penetrate, get to these, get to that soil and be able to, like I said, solubilize and remove it from the substrates itself. So they've come up with it. I mean, I can't get into the specifics on that, but for sure, the pH values are in the range of 7 to 8. It works very, very well. These are also inhibited products as well. And it kind of goes to some of the comments you made in the beginning of this podcast when you were talking about, the environmental, the whole Montreal Protocol, right? It was all based on ozone depletion in the atmosphere and all those kinds of things, right? Well, those arguments haven't really gone away. And you kind of mentioned that, this morning or earlier in this call. It's just that it's basically shifting now, right? So we've kind of solved that problem. And the next steps were to try and come up with a more user-friendly cleaning agent, which is what the pH neutrals are. In other words, they're not hazmat shipments, right? So they're much easier to ship. They're more user-friendly. They're less hazardous to use, and those types of things, right? And then also where we're going today is low VOCs. I mean, you sit in Los Angeles County, I think, right down in Southern California, and SCA-QMD has has the toughest VOC requirement or restriction in the country, if not in the world. So, the push today from, say, our perspective as a chemistry supplier or an engineer cleaning agent supplier to electronics marketplace is to help companies get to that next level. Go to any OEM tier 1 website, and they all have sustainability initiatives and objectives. And I'm not just talking about, like 14,000, well, ISO 14,000, of course, is part of it, but they're all about sustainability. So, pH neutral is part of that because you can avoid, neutralization of the wastewater, depending on what your process is ultimately looking like. Like I said, you have the more user friendliness of the people, shipping, costs are reduced, those types of things. And now if you pack onto that, being able to develop or put into the marketplace a true low VOC defluxing agent, it'll just meet that next level of requirement that's coming, from our industry. Take the EV industry, electrification of automobiles, case in point. I mean, they're all about environmental friendliness, right? And so if their manufacturers are using high VOC defluxing agents, I mean, you got to scratch your head and say, that doesn't kind of go along with our overall company, vision and mission here.
Sure. We're very rapidly running out of time, but I want to just touch this topic before I say goodbye. One of the most common questions I get asked is, how clean is clean? Or how clean is clean enough? And I think there are two answers. One is, if Eric is sending you an invoice, it's not clean enough. Right? So if Eric walks through your front door, your boards were not clean enough. The industry, IPC, one of our two major trade organizations, and the organization that sets standards, used to have an exact number on how clean was clean enough. And that was with the use of a resistivity of solvent extract tester or ROSE tester. And basically in imperial terms, that was 10 micrograms of sodium per square inch. Anything 10 or less, thumbs up, ship the product, it's clean. Anything greater than 10, thumbs down, don't ship it, it's dirty. And for those of you in the metric world, the rest of the world, that's 1.56 micrograms per centimeter squared. So I'll use 10. So 10 and above, 10 above 10, dirty, 10 or below, nice and clean. The irony is that that number never took into, first of all, it was developed in the 70s, and I would imagine that the people who worked on that number drove to work in their Chevy Novas listening to David Bowie on their 8-track tape player. That's the era that standard was, or the numbers that eventually comprised the standard was developed. And the number never considered the cost of failure. So, theoretically, a record player manufacturer who wanted to meet IPC standards would have to get the boards just as clean as NASA or Boeing or something, which is a little scary. It never considered the standoff heights. It never considered the density, because there wasn't a lot of diversity and density back in the 70s. All components were big and far apart. But it didn't consider any of those. It didn't consider the cost of failure. And it didn't consider the climactic and use environment. Everyone had the same number. Well, IPC took a long time, but they got the message, and they said, okay, we got to change this. This is not working. Because 10 for some people is like stellar clean, and 10 for some people is a death sentence, right? So it was no good. And now the new standard, which is freaking everybody out. Eric, I think you hear this quite regularly, and Sal, you probably do too. It's freaking. In fact, I know because I spoke with your people, Sal, about this very subject, and that is, what do engineers want? Give me a number. Tell me what I need to be. Tell me what number I need to hit, and I will find a way to hit that number. That number went away. The new cleanliness standard is now, this is IPC, and I'll paraphrase what IPC said. So IPC, how clean is clean enough? This is IPC. I don't know. You tell me. Just base the answer on objective evidence. And engineers are just like, what the heck is going on here? I want a number. And no, we're not going to get a number. You're going to give me the number, and you're going to prove how you validated that number. So we are running out of time, so I'll just say the standard requires that a test coupon that closely resembles the components that are on your board and the soldering materials that you will use to reflow your board, and the same profiles that are going to be used to reflow your boards, or as close as possible. You get this facsimile of your product, and you reflow it, and with all the materials, as you would in production, and then you put it in an oven with heat and humidity, and connect it to an SIR tester, surface insulation resistance tester, and you keep it in there for a week, 168 hours minimum. And if it doesn't fail from a resistivity standpoint, if the resistivity does not drop below 1 times 10 to the 8th, your boards are okay. The crystal ball has determined that your boards will more than likely not fail given a similar harsh environment, and you can ship the boards. If it fails, then you need to clean better. You need to do something, right? Change your design, usually clean better. So that is the pass-fail now, which means that maybe my board can get a 10, maybe Eric's board can get a 0.5, maybe Sal's board can get a 110 from a rose test standpoint. All of those are valid numbers as long as you can substantiate that number with objective evidence. So that's kind of, to me, every standard should be written that way, rather than coming up with an arbitrary number that usually is a result of several countries heard from, several input from commercial companies, from manufacturers, from users that all want the soften things up or strengthen things up depending upon the advantage it provides them. This is really quite objective. It's not subjective at all. It's very objective, hence the term objective evidence. But
very much so, Mike. And if I could just real quick, if anybody is, trying to meet that new J standard 001, well, it was actually released in Rev G, but Rev H builds on that in Section 8. Go look at that IPC WP019. It's in the B revision right now, and it is a very clear companion document. Basically, it's just, it's white paper document WP019. And it says, here's what changed in the J standard, here's why it changed, why it's changing for the better, and here's really how you create your own objective evidence. And example. Exactly. It gives you lots of examples I wrote a little bit. I wrote a few of those myself, and based on what we've done with our customers for years, because we would have customers come say, look, we passed the IPC, cleanliness requirement. Our board should not be failing. And I'm like, well, you can take that up with the IPC, I guess, because what you sent me was a charred hulk, skin of what used to be your product. So, I mean, sure, it passed, that criteria, but that clearly wasn't the right number for you. So, it really comes down to, doing your own homework, just like you mentioned, making sure that your number, however you're going to monitor, if it ROS or ion chromatography or any other method out there, you try to mash that up a little bit with your passing SIR, and now you've got a process monitoring data point that says my number is 0.5, it is 110 for sal. We've passed this 40 degrees C, 90% relative humidity, 168-hour test. Just you have to prove it to yourself. But that WP019, I like to guide a lot of people there, who are kind of newer to meeting criteria, and they say, what happened to the 1.56? And we say, well, it was never supposed to be used the way it was, finally overtaken, but by so many users say, well, we're going to use that as acceptance criteria. And that's never what it was supposed to be.
It was a 50-year accident, basically.
Yeah. Well, everybody was happy with it until they weren't,
Exactly.
but as miniaturizations, and complexities and things change, but why wouldn't the criteria change? That's just, it never made sense to me, even, from an outsider coming in, 23 years ago now, it never made sense to me that how does that same, number apply to everything? It's because you could meet it. It's not a hard standard to meet, 1.56. It makes it attainable, not the right number necessarily, but it might be. There's still a lot of people that are using that. Objective evidence can include historical, precedent showing we don't have a lot of failure related to boards that we tested to this standard for the last 20 years. So we're not changing anything. And the IPC said, great, go for it. That's your objective evidence.
One fly in the ointment there. Level 1 and level 2 changes. If you made any changes that fall under a level 1 or level 2 category, you got to go back to SIR. So you could, in theory, if all you've done is ROS testing and you've never had an ECM issue for 20 years, and you've never made a level 1 or level 2 change, and just to bring this out to make a point, a level 2 change is changing the production line your machine is on. If you move it from line 1 to line 2, that's a change that you have to go back and do some objective evidence. So, yes, that is true. I would love it if it weren't so strict from as an equipment manufacturer standpoint, right? But it is that way for a reason, as long as you don't change things. But a change, I can't think of 20 days that go by without someone stumbling over a level 1 or level 2 change, right?
Yeah.
And to your point on the white paper, if I only had $100 to my name and I had to buy the standard or the white paper, I would buy the white paper in a heartbeat.
Sure.
Because to me, the white paper references the standard and then provides layman explanations by example. And they use, for example, company A does this, company B does that, company C does this. And you will identify with one of the 4, 5, or 6 companies that they mentioned.
And they're all acceptable per the standard.
Absolutely. Absolutely. Yeah, I find the fuss is much to do about nothing. It really is a blessing in the form of a standard more than anything else, because at the end of the day, you're not out to check a box. You're out to ship products that's not going to come back to you, right? You don't want, whether you're mission critical and it can't fail, or you're a consumer product and it shouldn't fail. Either way, it's going to cost you time and money and reputation and potential liabilities and things like that. So at the end of the day, you're going to do it now, or you're going to get Eric. Keep Eric out of your office. I can say that with confidence because he's never going to run out of work. Never at all.
We are no longer, Terry Munson said he thought he'd be in business for 5 years, and that was 32 years ago.
Yeah.
He thought, well, the industry will catch on to this cleanliness thing, and we'll move on to something else. Here we are.
Yeah. Well, what we learn from history is we don't learn from history. It's just wash, rinse, repeat. To coin a cleaning term. Well, guys, this has been fun. I can talk cleaning all day long. So, and we didn't even hit some of the subjects. Maybe we need a part 2. I think we will come back. We won't wait 2 years or 3 years, however long it's been since I've talked about cleaning on this show. We won't wait that long next time, because it is a relevant topic. Obviously Maslow's theory, when you're a cleaning person, all you see is, cleaning challenges and opportunities. But it is definitely a growing subject. It's definitely mainstream again, or very near mainstream again. It's not
absolutely.
It's not a random process that's seldomly executed. It's common every day. I will, for my audience, I will provide Sal's and Eric's contact information. If you're listening to this on your favorite podcast app, just go to your app and look at the show notes, and you'll see contact information there. And if you're watching this on YouTube, just look down where it says Show More, click that, and you'll have access to Eric and Sal's contact information. Sal Sparacino, sales director at Zestron Americas, and Eric Camden, lead investigator, Foresight Laboratories. Thank you both for being my guests. Thank you both for agreeing to come on and talk about what you do, cleaning and failure analysis and things like that.
And
so I really appreciate
Mike.
it.
Yep. Thank you as well.
All right, guys. Take care.
All right. Take care. Bye-bye.
Well, that's another episode. Thanks for listening to or watching the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on Apple Podcasts, Google Podcasts, Spotify, Amazon Music, or virtually wherever you get your podcasts. Also, a special thanks to Circuit Assembly Magazine's PCB Chat at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Thanks also for your questions and episode suggestions. Please keep them coming. Send comments or episode suggestions to Mike at mikeconrad.com. Just remember, that's Conrad with a K. And be sure and subscribe to the podcast on your favorite podcast app. Or if you're watching our podcast on YouTube, click the subscribe button and the bell icon to be notified when new episodes are released. We release new episodes on the second and fourth Tuesday of each month. Once again, thanks for listening or watching. Stay safe, stay healthy, stay happy, and perhaps most importantly, keep doing it right. And I'll see you again in 2 weeks.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.